one of the features of complex ions is that they quite commonly undergo substitution reactions in which one or more ligands in the original complex get replaced with different ligands. And these kind of reactions, called ligand substitution reactions, are something you need to know a bit about, and this is an important part of the transition metal chemistry you learn. So ligand substitution reaction just means a reaction where one or more ligands from a complex ion are replaced by different ligands. And that can happen for various reasons. As we've mentioned, water is not particularly good at donating one of its lone pairs to form a dative covalent bond. So if you add to the solution things that are better at forming dative covalent bonds, like ammonia, or negative ions like chloride, they will often kick out the waters and replace them just because they can form stronger bonds. In other cases, ligand substitutions happen just for statistical reasons. If your original complex has ligand molecules which are present in quite low concentration in the solution, you can overwhelm them by adding a much higher concentration of a different ligand, and they may then just, through competition, kick out the original ligands just because of the higher concentration. So those are the two reasons why ligand substitutions sometimes happen. So there are a few ligand substitutions that you need to know about in a bit of detail. The first example that you specifically need to know of a ligand substitution reaction is what happens when you add a high concentration of chloride ions to aqueous copper 2+. So here's our starting solution, which is the characteristic blue color that you see in copper sulfate solution, and that's the hexa aqua copper 2+. And if you add chloride ions, you start to see the color changing, as you can see in the picture. So what we're adding here is concentrated hydrochloric acid, but it's important to realize the fact that it's an acid is irrelevant here. It's the chloride ions in that acid that are replacing water molecules gradually and causing the color to change. So what you end up with finally is this solution, which in the picture looks a bit green, but it's actually kind of a slightly greenish yellow color, and if you just call it yellow, that's fine. And that's this ion. So it's got 4 chloride ions and 1 copper 2+, so the overall charge is 2-, and that ion is described as yellow. And in between, of course, you have a mixture of both, because this is a reversible reaction. Remember, you've got an equilibrium, and here the equilibrium, if you like, is far over to the left, here it's far over to the right, and here it's somewhere in between. So the color you see is a mixture of blue and yellow, and it therefore looks green. So you need to know these colors, that CuCl4 2- is yellow, and that it's formed by this ligand substitution reaction. So there it is written as an equation, and these ligand substitution equations are things you're highly likely to get asked to write out. So it's reversible, so you have the reversible sign here, and what you always do is literally just have the original complex ion and then whatever ligands are going to substitute into it on the left, and then the new complex ion and whatever ligands have been kicked out on the right. So they're very easy equations to construct. And because they're reversible reactions, you can apply Le Chatelier to thinking about what's going to happen. So for example, if you increase the concentration of chloride ions by adding more conc-HCl to the mixture, the equilibrium shifts to the right to oppose the increase in chloride concentration, and that's what drives the color change from blue towards yellow as the equilibrium shifts to the right to oppose the change. Equally, if you decrease the chloride concentration by, for example, precipitating chloride out of the solution, the color will revert to blue because the equilibrium will shift back to the left. Second example you need to know is a little bit more complicated, and that's what happens when you add ammonia to aqueous copper 2+. So again, you get a color change, but here it's from the normal aqueous blue color, to a much deeper blue colour. So the colour change you have to learn is from blue to deep blue. And what's happening here is that, again, you're kicking out water molecules, but you get a more complicated situation. So 4 ammonia molecules kick out 4 water molecules. But the complex ion you end up with is still octahedral. It still has a coordination number of 6. It's just that 4 of the ligands are now ammonia and the other 2 are still water. The reason it does that, again, is a complicated quantum mechanical reason. It's due to something called the Jahn-Teller effect, if you want to look it up, but you absolutely don't need to know that. You just have to learn this ion. So it's got a quite complicated looking formula, because you've got copper 2+, 4 ammonias, 2 waters, and because all the ligands are neutral, the overall charge is still 2+. So that's your deep blue complex ion that's formed here. And that will have an octahedral shape because you've got 6 ligands around it. So it's different from the chloride case where you get a tetrahedral ion being formed. So both of those are examples of specific complex ions which you actually need to learn. Here's the third one. So this is adding ammonia again, but this time to aqueous chromium 3 ions. So here's our starting point. In this case, I've got a green version of chromium 3+ illustrated. Remember, that ion, the hexaquachromium, is actually violet, but you don't very often see that. Most commonly, chromium 3+ already has 1 or more negative ions from the existing solution incorporated into there, and that turns it green. So if you say either violet or green for the chromium 3+, they'll be happy with that. But when you add ammonia, the colour changes to this purple colour. And in this case, it's more straightforward than with copper 2+, because all 6 of the water molecules are replaced with ammonia molecules. So it's a straight swap. 6 ammonias in, 6 waters out, changes the colour from violet or green to this purple colour. And again, you need to learn the colours and you need to learn the formulae so that you can write the ligand substitution equation. So that's 3. An example of a ligand substitution reaction which is hugely important in real life is the function of hemoglobin. So hemoglobin is what carries oxygen around in your bloodstream, and it's a big protein molecule, but it includes an Fe2+ ion, which can use oxygen as one of its ligands. And so what you get is a ligand substitution reaction in which oxygen can replace water as one of the ligands around an Fe2+ ion. So you don't need to know all the detail of this at all, but this is how the Fe2+ is actually bound in hemoglobin. You can see this is a tetradentate ligand, which is the heme group. So you've got 4 nitrogens surrounding it. The ion is actually 6 coordinate. The 5th position is taken up by one of the side chains of the protein, but it's the 6th position, which in the absence of oxygen is water, and in the presence of a high concentration of oxygen, that water is kicked out and replaced by an oxygen acting as a ligand. So we can sort of write this as a equilibrium. So if we use H to represent hemoglobin, we've got H2O plus O2 can undergo this substitution reaction to give O2 plus water. Okay, so it's just a simple ligand substitution like that. And again, Le Chatelier applies. So if you're in the lungs, the oxygen concentration is high. So Le Chatelier says the equilibrium will shift to the right to oppose the increase in oxygen concentration. So the hemoglobin picks up oxygen in the lungs. If you're in somewhere where there's lots of respiration been going on, like a contracting muscle, the oxygen concentration will be low, and so the equilibrium will shift back this way and more oxygen will be released, and that's how hemoglobin does its job. So say you don't need to know any structural details, but you need to be able to describe this kind of equilibrium and know that it's oxygen competing with water for the binding site of an Fe2+ ion. The other related issue to that is that carbon monoxide can also compete with oxygen or water for that binding position. And the problem with carbon monoxide is that it's much better as a ligand than either oxygen or water, forms stronger dative covalent bonds. So what can happen then is that you have another binding equilibrium where you can form hemoglobin bonded to carbon monoxide, plus I guess O2 it would be kicking out in this case, and that is very stable. So once the carbon monoxide's bound, it's very difficult to get rid of it and replace it with oxygen or water again. And so it basically takes the hemoglobin out of commission. It can't carry oxygen around anymore, and that's why it's so toxic, because it prevents you delivering oxygen to the tissues. So again, you need to know that carbon monoxide undergoes a ligand substitution, kicking out either oxygen or water, and basically then staying there, because it's very difficult to outcompete it. The way carbon monoxide poisoning is treated is to put the patient in a chamber with a very high pressure of oxygen. And then again, it's just a substitution reaction, that if the concentration of oxygen is high enough, it can start to compete out the carbon monoxide, and the carbon monoxide eventually gets breathed out. So it's all ligand substitution reactions. So you just need to know that little bit, not the structural detail, but hemoglobin, oxygen acting as a ligand to Fe2+, and competing with water, but also potentially with carbon monoxide. So now you can do a question relating to ligand substitution, which is question 6 in the pack.